All right, the last time we met, we talked about all the things that we could do with the first derivative or the first derivative test, namely find absolute extrema or what's called a max or min point. I meant relative, excuse me, relative or local extrema, and that just means relative or local max or min points. And the other information we could find using the first derivative test is areas of increasing where our graph or our function is increasing or decreasing. So just from that, taking that first derivative, we were able to find a lot of useful information about how our graph behaves. Now, if you take the derivative again, then that too also reveals a lot of helpful or useful information. So let's talk about what the second derivative test reveals. And I'm going over these terms with you guys in just a minute. The second derivative test, or you take the derivative the second time of your function, the second derivative test determines what's called concavity and also inflection points, if they exist. So that's what the second derivative test reveals about the behavior of our function, concavity, and also, if they exist, any inflection points. Inflection points you may also see in like other resources, these referred to as turning points. So those mean the same thing. Now, a function is concave up if it looks like this. If it looks like a regular shaped cup, then this is known as concave up. And if your piece of the graph is upside down, then that's known as concave down. Now, calculus-wise, you still need to get your critical point or points by setting your derivative equal to 0. So that part hasn't changed. You set your derivative equal to 0 to find your critical points. There may be one or there may be several. Now, calculus-wise, remember with the first derivative test, if you see a plus sign on your sign chart, then that meant the interval or intervals where your function is increasing. If you saw a negative sign on your number line / sign chart, then that means the area or areas where your function is decreasing. The plus and minus signs also tell us things about concavity. So if you have a plus sign, or if your second derivative is positive or greater than 0, then that means the interval or intervals where your function is concave up. Now, on your number line slash sign chart, if you see a negative sign, that means your second derivative is less than 0. And that indicates that your function is concave down at that particular interval. Now, let's say you have a graph that behaves this way, just a basic curve. Now, anytime you go from concave down or concave up to concave down or concave up or vice versa, anytime your graph changes concavity, the point where the graph changes concavity is known as the inflection or turning point. So the inflection or turning point is the point where your graph changes concavity. It could be concave down to concave up, or concave up to concave down. Now, you may not with every single function, there may not be an inflection point. Just like with some first derivative tests, you found a relative min, but there was no relative maximum point. So not every single function has a turning point. Are there any questions about the definition of concavity or inflection point? Okay, I'm going to start with the basic function that we all know. And we're going to use both the first and second derivative test to get all the characteristics of our graph. So we have f of x equal to negative x squared. And we want to find all of the key characteristics of our graph, namely relative max or relative min if they exist, areas of increasing or decreasing, and remember, all of this information we can find using the first derivative test. So let's take the first derivative of our function. F prime of x is equal to negative 2x. Now, the next step is to find any critical points. So to find any critical values, you set your derivative equal to 0 and solve for the given variable. So when we solve for x, our only critical point is x equal to 0. What we do with that critical point is put it on our number line. And our critical point, once we plotted it on our number line, has split our number line into two intervals. So we need to test everything less than 0 and test everything greater than 0. So we need 2 test points. Something less than 0, let's try -1. And something greater than 0, let's try +1. Now we're plugging these into our first derivative. So when we plug in -1 for x, we get a +2 or plus sign. So everything to the left of 0 is positive. When we plug in +1 for x, we get -2. That means everything greater than 0 has a negative sign. Now, anytime you go from positive to negative, that indicates a maximum, a local maximum point. So our relative maximum point is at 0. And to find the y value, just go back to your original function and replace this x with 0. So our relative maximum point happens at the ordered pair 0, 0. There is no relative minimum point. Next up, we need to find where our graph increases and decreases if possible. On your sign chart, the plus sign indicates an interval of increasing. So since that's less than 0, our graph increases from -infinity to 0. Now, the negative sign on our sign chart for the first derivative test indicates where our graph decreases. So since that's greater than 0, the interval decreasing would be from 0 to positive infinity. Now, before we use the second derivative test to find the rest of our graph's characteristics, are there any questions about the information so far? Now, to find the other characteristics, namely possible concavity or turning points, we must take the second derivative. So the derivative of -2x is just -2. Anytime you get a constant for a derivative, then if it's the first derivative, this means your graph is always decreasing if it's a negative value, or always increasing if your constant's positive. What this means with the second derivative test, because our second derivative is negative, that means our function is always concave down. Now, if it's always concave down, then that's all real numbers, or the interval from -infinity to positive infinity. So that means, logically, if our graph is always concave down, then it's never concave up. And to find the possible turning point or inflection point, we would need to find the critical value. Well, there's no critical point here because our second derivative is constant. So there are no inflection points either. Now, if you were to graph this on Desmos, it will look something like this. It will be a upside down parabola. And right away, we can see that our maximum point is correct. That occurs at 0, 0. There is no local minimum point. Our graph increases from negative infinity to 0. That part's fine. And according to our first derivative test, our graph should decrease from 0 to positive infinity. And that's also true. So everything we found with the first derivative test matches our graph. Now let's check out the characteristics for our second derivative test. It's never concave up, so that part's fine. There is no turning point or change in inflection, so that's correct. And our graph is always concave down from negative infinity to positive infinity. That also checks out. Any questions about the first or second derivative test? You got it okay? I mean, did you get the picture of it on your phone? Okay, good deal. All right, let's look at another question. We have f of x equal to 1/3 times x cubed minus x. And we need to find, starting with the first derivative test, we need to find all of our information, namely relative max or min, maximum or minimum point, where our function is increasing and or decreasing. So we can find out all this information using the first derivative test. All right, so f prime of x. When you take the derivative of 1/3 x cubed, you're using the power rule, meaning the original exponent moves to the front and it's being multiplied by the 1/3. Those threes cancel each other out. And when you subtract 1 from the original exponent, you get x squared. And the derivative of negative x is -1. The next step is to find our critical value or values. So we set our derivative equal to 0 and solve for x. You can take the square root of both sides. And when we take the square root of 1, remember we get two answers, a -1 and a +1. So let's put those critical points on our number line. Now, our critical points split our number line into 3 separate intervals. So we need to test everything less than -1. We need to test everything between -1 and 1. And we need to test the interval greater than 1. That means we need 3 test points. All right, something less than -1, let's say -2. A number between -1 and +1, 0. And a number greater than 1, let's try 2 as a test point. Now we are plugging these test points into our first derivative. So starting with -2, that gives us 4 minus 1, or +3. So anything less than -1 has a resultant sign of a plus. Now let's test the interval between our numbers by plugging 0 into our first derivative. So that gives us -1, meaning the resultant sign between our numbers is negative. And finally, when we plug in 2 into our first derivative, we get 2 squared minus 1, and that also gives us a +3. So we'll add our plus sign right there. Now the signs on our number chart tell us a lot about our characteristics of our graph. Right here, anytime you go from a positive to a negative sign, excuse me, that indicates a relative maximum point here. And going from negative to positive, that indicates a relative minimum point at 1. All right, so we have a relative maximum point at x equal to -1. And whatever the y value would be, let's see here, 1/3 minus 1. Your y value, when you plug in -1 into your original function, you end up with -2/3 for y. Oh, sorry, no, that is wrong. Got my signs mixed up here. Sorry about that. Let's see, -1/3 plus 1. That would be a +2/3 for y. Now you also have a relative minimum point at x equal to 1. So when x is equal to 1, plug in 1 everywhere you see an x in your original function. And when you do the calculations, you should get negative 2/3 for y. Now, the plus signs are where your function increases. And that happens from negative infinity to negative 1. And also from 1 to infinity. Now, the negative sign on your sign chart reveals where your function is decreasing. And that happens according to your sign chart between the numbers negative 1 and 1. Before we find the rest of the graph's characteristics, are there any questions about first derivative test? All right, let's use the second derivative test to find the rest of our characteristics. So when I take the derivative again, f double prime of x is equal to 2x. Now we still need to, regardless of what test you're performing, we still need to find the critical points or point. So set your derivative equal to 0. And our only critical point is 0. So let's plot our critical point on our number line. And our critical point, when we plotted it, split our number line into 2 intervals. So we need 2 test points. Something less than 0, let's use negative 1. And something greater than 0, let's use positive 1. Now you plug these into your second derivative. So when we plug in negative 1, we get negative 2. So anything less than 0 has a negative resultant sign. Now when we plug in 1 to test greater than 0, we get 2 times 1 or positive 2. So anything greater than 0 has a positive result sign. Now, with the second derivative test, anytime you see a negative sign, that tells you where our function is concave down. So that happens everything less than 0 or from negative infinity to 0. And the plus sign on our number line for the second derivative indicates where our function is concave up. So that happens everywhere greater than 0 or from the interval 0 to positive infinity. Now for this problem, there is an actual inflection point. Anytime you have a sign change on your number line, and it can be from negative to positive or positive to negative, that indicates an inflection point. So we have an inflection point as at x equals 0. To find your y value, you just plug in 0 everywhere you see an x in your original function. So when we plugged in 0 for x, y is also 0. Any questions about what we got from the second derivative test? I'm switching to Desmos for just a second to see if all of our characteristics are correct. So give me just a second. And let's type in our graph, our function, I'm sorry. F of x equal to 1/3 x cubed minus x. And let's hide everything and show the graph. All right, we got a relative maximum when x is -1. So that part is correct. -1 2/3. And we find a relative minimum point occurs at 1 and -2/3. So our relative extrema are correct. Now, we also found out that our graph is increasing from negative infinity up to -1, and also from 1 to positive infinity. So that part matches perfectly. And the last thing we found from the first derivative test is that our function is decreasing from -1 to +1. And that is also true. Now, moving on to the information we got from the second derivative test, we determined our function is concave down from negative infinity to 0. So as you follow my arrow, this is definitely concave or upside down. And we also determined that our function was concave up from 0 to positive infinity. Concave up looks like a cup, really. The last bit of information we determined is we have an inflection point at 0, 0. That is true because this is where we go from concave down, it changes to concave up. So 0, 0 is the correct turning point. All right, let's look at another problem. In which we are finding a whole bunch of information. Given f of x equal to x to the 4th power minus 4x cubed. We need to use the first and second derivative test to find all the characteristics of our function's graph. So the first step is take the first derivative. So f prime of x is equal to 4x cubed minus 12x squared. Now, before we find our critical values, let's pull out a GCF. So the GCF is 4x squared. And what's left in our parentheses is x minus 3. Now we can set our first derivative equal to 0 and find our critical points. Now you can set each part equal to 0 or use opposite signs for part of it, but you'll end up with the following critical points: 0 and positive 3. Now let's plot our critical points on our number line. And our critical points split our number line into 3 intervals. So that means we need 3 test points. Something less than 0, let's try -1. Something greater, well, between 0 and 3, let's try 1. And finally, something greater than 3, let's try positive 4. And you can either plug these into your original first derivative or your factored first derivative. I'm going to use the factored part. Actually, it doesn't matter. I think I'll use the original. Now, when you do the calculations, you end up with -4 minus 12, and that gives you -16. So that means anything less than 0 is a negative result sign. Let's test the middle interval by plugging in 1 for our first derivative. And that gives us 4 minus 12, which is a -8. So still, anything between 0 and 3 has a negative resultant sign. And last, let's test the interval greater than 3 by plugging 4 into our derivative. And I'll go ahead and tell you, when you do the calculations, you'll end up with a positive integer. So that means everything to the right of 3 or greater than 3 has a positive sign result. Now we're ready to use our sign chart to get our first part of our characteristics of our graph. Actually, there is no relative maximum point because we don't have any signs that go from positive to negative, but we do have a relative minimum point because we have a sign that goes from negative to positive. So that indicates a relative minimum point at x equal to 3. And I don't know what the y value is. Let me figure it out right quick. Let's see, 3 cubed is 27 times 4 is negative 108 plus 81. So if I put this in my calculator correctly, our y value to our minimum point is negative 27. Now, our graph, based off the negative signs, is actually decreasing from negative infinity to positive 3. And the plus sign on our first derivative sign chart indicates where our graph is increasing. And that happens greater than 3 or from 3 to positive infinity. Now, before we use the second derivative test to find the rest of our graph's characteristics, any questions about the first derivative test? All right, let's do the second derivative test. So when I take the derivative again, and I'm taking the derivative of this part here, that gives us 12x squared minus 24x. Before we find our critical values, again, factor out the greatest common factor. And that's 12x. And what we're left with is x minus 2. So our critical points, when you solve for x, are 0 and positive 2. What we do with our critical points is put them on our number line. And again, our critical points split our number line into 3 separate intervals. So that means we need 3 test points. Something less than 0, let's try negative 1. Something between 0 and 2, let's try 1. And a number greater than 2, let's try 3 as our test point. Now you can plug these test points into your original second derivative or your factored version. I'm still using the original. So when we plug negative 1 in first, that gives us 12 plus 24, positive 36. So everything to the left of or less than 0 has a positive sign result. Now to test the interval between 0 and 2, let's plug in our next test point, 1. That gives us 12 minus 24, or negative 12. So the result sign between 0 and 2 is negative. And finally, let's test the interval greater than 2 by plugging in our third test point, positive 3. And that gives us 108 minus 72, which is again positive 36. So everything greater than 2 has a positive sign result. Now we are ready to get the remaining characteristics of our graph. Remember, for the second derivative, anytime you see a plus sign, that indicates intervals where our function is concave up. And that happens from negative infinity to 0, and also from 2 to infinity. So that's the intervals where our graph is concave up. And remember, the negative sign for the second derivative indicates where your graph is concave down. And that only happens between the numbers or the interval from 0 to 2. Now, anytime you have a sign change, it doesn't matter if it goes from positive to negative or negative to positive, that means you have a point of inflection or a turning point. So we actually got 2 turning points here, at 0 and also at 2. So let's find these two turning points. Well, to find y when x is 0, that's easy. Y is also 0. And our second turning point or point of inflection occurs when x is 2. So when x is 2, we got, I'm figuring this in my head, so be patient with me. Let's see, 4 times 8. So the y value for your second turning point is negative 16. Are there any questions about the first or second derivative test? This is the first derivative test, and this is the second derivative test. Now let me switch back to Desmos and check all of our graph's characteristics. So hang on 1 second. And let's type in our next function. X to the 4th power minus 4x cubed. And let's hide everything and reveal our graph. All right, first derivative stuff. There is no maximum point. That's true. Let's see here. Oh, I did not zoom out far enough. Our relative minimum point is way down here, and we determined it to be, 3, -27. So the relative minimum is correct. We said our interval decreases from negative infinity. Okay, that's way up here. From negative infinity all the way down to 3. So that part is good. And we also said, based off the first derivative test, that our graph was increasing from 3 to positive infinity. So that part is also good. Second derivative test, we said our graph was concave up from negative infinity to 0. So that's that little piece right here from negative infinity to 0. It's a cup turned right side. And also from 2 right here almost. So from 2 to positive infinity, that's also where our graph is concave up. So the second derivative test, the information for concave up checked out. Now, according to our second derivative test, our functions should be concave down from 0 to 2. Yep, it's upside down from 0 to 2. So that checked out just fine. Now, the last thing we need to check is our turning points or inflection points, and we've found 2 of them. One is easy to see. This is 0, 0. It changes from concave up to concave down. So that matches what we found. And there was another one we found at 2 and -16. And let me, right there. Going from 0 to 2, which is concave down, and then it's going concave up again. So our turning point here at 2, -16 is also correct. Are there any questions about finding any characteristics of a function's graph? I will, once the video is done processing, I will, oops, I'm sorry. There you go. Once the video, well, dang. Try that again. Okay, here's the last question if you need to look at it again. Um, as I said, once the video is done processing, I'll either post it on the announcements page in Blackboard, either later on today or first thing tomorrow.